So now we can look at guitar strings. So immediately I want you to realize that I put the source up here, and that's because I actually got this from Jay Lehman's book, okay, on applications. And then he cited a good reference of Garland and Kahn and Math and Music. Okay, so I do need you to know that there's this thing that happens in academia and in industry and in the government, everywhere, in every sector of our society, where we give credit to those who actually made discoveries, okay? And this is called, if we write down that we came up with it, we are plagiarizing. So that's kind of cheating, yes? And within our legal system, that's actually built. It's called patents, right? If you come up with it, then you get credit for that. And then it becomes part of what everybody knows or experiences. So I just wanted to make a shout out for him crediting these authors for realizing this, and then within his own book. Yes? So, and I also want you to realize by now that really we just have a data set. We run an experiment, have some data, and then we graph every which way we can to see if we can visualize a relationship between two quantities. Okay, so let's do it. This is guitar strings. And here's the effective length, and that corresponds to certain notes like A sharp, etc. I notice, whatever, I'm not going to talk about that. And the inches, okay, so let's actually read this. When the second thickest guitar string is picked, it vibrates at a frequency of about 110 hertz, or it vibrates 110 times per second. By pressing firmly on the fret, the player is shortening the string. Okay, so if you didn't, and it was 25.5 inches long, and you plucked it, this is the frequency at which it would vibrate, right? But then as you shorten the string by holding it down, so you're shortening the string length, it's going to vibrate differently. And as it vibrates faster, the pitch becomes higher, a higher pitch sound. As a result, frequency increases and pitch comes out higher. Okay, so I made the decision that I believe that the length of the string is explaining how quickly it's moving, and then that is explaining the pitch. So that the frequency is responding to the length, or you putting your finger on it and shortening the length of the string. So I went ahead and put this in list 1 and this in list 2. Okay, let's create a scatter plot. Okay, so just so that you can see that, list 1, list 2, length and vibrations. Okay, so now we go back to y equals, we need to clear out what we had done before. Second stat plot, turn it on. It's on scatter, and now I want list 1 and I want list 2. And then I go to zoom and I go to 9 for a statistics plot. Woo! And there it is. Look at that. You might think it's exponential decay, but I can clearly see that it is doing this boundary business that the inverse model has in store. Okay, so create it, draw it, label it. Okay, so explanatory variable, length of string in inches. And frequency of vibration in hertz. Got it. They call it the effective length. They mean you're holding it down so it's not that long anymore. It's this long. And the image, oh, there's so many data points on this one. Roughly like that? Okay, got it. So there's our scatter plot. And, oh, it actually says create an inverse variation model. Huh, la-di-da. But I do think that that is a good decision because I think linearity is out because it has curvature. I think that it doesn't have a rebound, and it definitely looks like it doesn't have an initial value, and that it fits the inverse model very well. Okay, so I think this is a good decision. And, oh, I remember this was actually tricky because there was no button for that. So let's go back and remember that really quick. So remember stat calc. There's a linear, a quadratic, cubic, quartic, linear, natural log, exponential, power, logistic, sine, but no inverse variation model. Okay, so I'm remembering how we go about this. The first thing that we did was we wrote down that an inverse variation model says that the frequency then would equal k divided by the length. Okay, so just the model's format where k is some constant. And then I remember we found the constant by finding an average. Oh, we multiplied. Ooh, so multiply, scale up both sides by, okay, hold on, by L. Oop, YV. Not a V. Not a V. It's a length. Okay, scale up by the length, and that will equal K. Okay, so I remember now we created a new list that had the frequency times the length. Here we go. Okay, so just so that we're crystal clear, I am doing L3 equals L1 times L2 right now. Okay, stat, edit, go up to list 3, hit enter, and now in there, put L1, which is second 1, times second L2, or second 2, which is L2. And it populates everything. So multiply these two values, 25.5 times 110 is 2,805. And then we found the average of these. They're all looking very similar, I see. Okay, stat, calculate the average of list 3. And we get an average of 2,805.2. Okay, so after we did this, we found the average of L3, and we ended up getting F is approximately equal to 2,805. We can go 0.2. 2 decimal places, 0.21 divided by the length, where F equals the frequency, how quickly it's vibrating, and L equals the length in inches. Okay, graph your model with your scatter plot. Let's do that. 2,805.21 divided by x, which will represent our length, and we graph. Wow, great model, great model. Okay, so it actually traveled through every single one of these. So this was a good decision. To model our data with the inverse variation model, that was a good decision, just based on this and the correlation. Use your model to estimate the frequency of guitar string length of 7.58 inches. Okay. Oh, and now when I think about this, I even think about pianos, right? Okay. Nonetheless, this is length. I'm labeling this with the correct amount this time because last time that got me in trouble. The length is 7.58. Estimate the frequency. Frequency is approximately 2,805.21 divided by 7.58, and that 2,805.21, what is this? Divided by 7.58, that is about 370.1 hertz, or vibrations per second. So we just used our model to estimate the frequency, so a lot. This is a short one and it's vibrating a lot at a high pitch. Use your model to find what string length is for the pitch of A, an octave, I think this is supposed to be above. Oh boy, look at me. An octave above the ones on the table. And it tells us that that A has a frequency of 440. Okay, so we're saying in our model the frequency is 440 is equal to 2,805.21 divided by the length. I'm going to scale both sides up by L. So that means that, and this is called viewing division as a missing factor problem, right? I don't know why I put a line over it. It's fine for now. But if 2,800 divided by L equals 440, then 440 times L is equal to 2,805, right? So, scale down. Scale down by 440. And then we will see our length, how many times it went into there. So, 2,805.21 divided by 440, and we get L is approximately 6.38 inches long. Okay, so if it has a higher pitch, it's shorter in length. Got it. Okay, so as a quick summary of everything that we just did, first we had to input the data, then we made a scatter plot, then we chose a model, then we wrote our model and we made sure it fit, right? After making sure it fit, we had to look at what we could do with that model. For instance, if it was a quadratic, we could use a quadratic formula. But then we went ahead and we used those models to make inferences that maybe weren't in our data chart, or even to show how much error our model actually had, okay? In general, it all starts with a data set, and then we just graph it to see what works best. How can we make the best guess we possibly can?